pick up where we left off on Wednesday. That was a long time ago. What were we doing? We were trying to prove senses in which clustering, grouping points meaningfully, is hard only when it doesn't matter. Meaning when it matters, it's easy, right? That's the contrapositive. What does that mean? Well, by it mattering, it means there's sort of some clustering, some meaningful groups that is there to be found, and maybe if we really articulate that assumption precisely, it will imply structure about the input, which we can then actually provably make use of in an algorithm, okay? So we executed that on Wednesday, and we're going to do it again today, okay? So it's going to be a different model, it's going to be a different algorithm, and I'll explain in a second, why we might want to do this exercise twice, okay? There's a lot of different reasons, all right? We're going to study the exact same clustering problem even as Wednesday, although let me say now, almost everything we say today carries over to other popular clustering objectives as well, like k-means. But I just want to keep things focused. We're going to keep talking about the k-median problem. To remind you, the input is a metric space, finite, so n is the number of points x. What does it mean it's a metric? Well, the biggest thing is that d, this distance function, satisfies the triangle inequality. So we used that over and over again on Wednesday. We're going to use it over and over again today. Okay, so d satisfies the triangle inequality. Shortest distance between 2 points is a straight line. Intermediate destinations only makes it longer. What's the objective function? Your responsibility is to choose k centers, so k out of the n points. And and then what you think of is you think of every point in the metric space being assigned to its closest center, and you want to minimize the sum of everybody's nearest neighbor distances. Okay, so sum over the n points. For each point x, you look at which of the k centers is closest to it, you look at that shortest distance, and you sum up those n numbers. Okay, so that's what we want to do. We want to choose the k points to make that as small as possible. So I was doing this Wednesday, but let me just sort of remind you, I'm going to be a little sloppy about talking about clusters or clusterings and talking about a choice of centers, okay? So in the k-median problem, if we choose centers, that obviously induces clusters according to who gets assigned to which center when we assign them to their shortest centers, okay? So a cluster is just around center I is just the points for whom center I is the closest. Similarly, if I give you clusters, you can easily just pick which the best center separately for each cluster, okay? So you can go from clusters to centers and back. So I'm just going to be sloppy about that, okay? So let me tell you about the restriction on input, the stability notion that we're going to be doing today. And it shares some of the spirit of Wednesdays, but it comes from a slightly different motivation, and it is technically different. So here's what it is. So we're just going to assume, first of all, that our target clustering, what we want, is the numerically optimal solution to this objective function. Okay, that's the first thing. So last time I made a distinction between a target clustering and the one which happens to optimize the objective function. Here, we're definitely going to assume they're the same. And actually, we're going to assume something much stronger than that. We're going to assume that the target clustering, and call its clusters C star 1 up to C star k, remain optimal under many different perturbations of the input. Okay, and remember the input is really this distance function d. So not only is it optimal for the distance function d, but also for many other nearby distance functions. So precisely, under any what I'm going to call a gamma perturbation, and in general I'm going to call this notion gamma stability. And by gamma perturbation, I just mean for each real distance dxy, for the purposes of thinking about whether this clustering remains optimal or not, you're allowed to perturb the distances. Where here sigma is some number between 1 and gamma. Okay? So if gamma is 3, for example, with a gamma perturbation, for each of the n choose 2 distances, you're allowed to independently make a choice of how much to blow the distance up. Okay, I'm not going to allow you to shrink it, but you can blow it up. You can blow it up by most a factor of gamma. Think of gamma equal 3. Okay? One comment. So for the original input, we're assuming it's a metric space. So D satisfies the triangle inequality. After you do some perturbations, it might not satisfy the triangle inequality. Indeed, just think about a triangle, 1, 1, 1. If you make one of those a 3, all of a sudden it's not satisfied anymore. That's okay. Okay? We're going to allow that. Okay? So we insist that opt remains optimal even under gamma perturbations that do not result in a metric distance function. Okay? So that's an assumption. Right? So an instance, a k-median instance which satisfies this property is called gamma stable. So as we take gamma bigger and bigger, does this constraint get more or less stringent, more or less demanding?
More demanding.
More demanding, right? So we're asking more from the instance. So in other words, fewer instances will satisfy this property as we take gamma higher and higher. So the computational problem is easier and easier for bigger gamma. Okay? So what we're wondering is if there's some magic value of gamma that's sufficiently large that we can actually solve these problems in polynomial time. Okay? And that's what we're going to quantify today. Okay? Look at the gamma which is sufficiently large so that k-median goes from NP hard, which we know it is in general, to polytime solvable. Okay? So that's the technical problem. Let's talk a little bit about motivation. So, I mean, just like Wednesday, the authors were intending to articulate an assumption which is generally implicit when you run clustering algorithms, and then make it precise and ask if taking that assumption literally results in easier instances. But they're doing it for a slightly different implicit assumption than on Wednesday, so we're getting a slightly different mathematical definition. So on Wednesday, we had this C epsilon notion of stability, and there the implicit assumption was that if you ran a good approximation algorithm, a C approximation algorithm, you'd be happy with the result, in the sense that it was almost the target clustering. So that resulted in this formal definition saying numerical approximation of the objective function better implies structural approximation of the target clustering. Okay? So that was the implicit assumption we were formalizing on Wednesday. Here it's a different one. Here, really the motivation is, well, think about these k-median problems. Okay, they're specified by this distance function d. Where does d come from? Okay, sometimes maybe you're literally thinking about points in 3 space or n space, and Euclidean distance is exactly meaningful. Often in say unsupervised learning applications, that's not what d is. Okay, x and y are not points in space. X and y are images or documents or proteins. Okay, and there isn't some canonical, obviously correct way to assign distance or dissimilarity between 2 objects. You probably came up with a formula or an algorithm which, when you run it on 2 images or 2 proteins or 2 documents, gives you a number, but there's aspects of that algorithm that are going to be ad hoc, okay, that you're not fully confident about. You can imagine a slightly different algorithm being just as meaningful. Okay? So if you have one of these heuristically defined distance functions and then you're solving the induced clustering problem, tacit in your mind for this to be a worthwhile exercise is the idea that the answer to this clustering problem shouldn't be highly dependent on exactly what the distance function is. Right? So if you tweak, if you hard code one parameter in your distance heuristic function slightly differently and you start getting 1.1s instead of 1.05s, hopefully you get basically the same clustering back. Right? So because D is heuristic in these applications, you want the answer to be robust to perturbations in D. Right? So that's where this comes from. Okay? In clustering problems you really want to solve, that's often what you're sort of hoping is true. And again, in the spirit of Wednesday, they're saying, let's really write that down as a mathematical definition, look at the instances that conform to it, and study the complexity of that special class of instances. Yeah.
We assume that exactly the same clustering is still optimal.
Good question. So I'm going to spend the lecture on the simplest version of this definition, where unlike Wednesday, where we allowed a few points to be classified incorrectly, today I'm going to ask you get every single point correctly. Okay? There is recent work which relaxes this in the way you'd expect, given what you saw Wednesday, and says, well, you move the d's by gamma, and opt only changes on an epsilon fraction of the points. Similar statements are true via similar algorithms, similar arguments. All of it's more complicated than what I'm going to talk about today. But the algorithms are in a similar spirit, the proofs are in a similar spirit, the constants are worse, and you need a big clusters assumption like Wednesday, which we won't need today. Okay?
This assumption is extremely stringent.
It is stringent. It is stringent. But as we'll see, it's not, it doesn't trivialize the problem. Okay? Especially as you think about varying gamma, there's actually going to be interesting regimes under which the problem is sort of trivial, solvable but not trivial, and then unsolvable, meaning NP hard. Okay? So gamma gives us a nice sort of parameter to play with, how much stability you need to imply tractability. But absolutely, I mean, the epsilon equals 0, if you like, assumption is a strong one, but that's going to make it so I can make all of the points I want to make in this lecture as cleanly as possible. And there is work without that assumption. Okay, so motivation, distance function is often heuristic, and so you want robustness with respect to it. So you're thinking about that being a sort of, that's a property you're really hoping your clustering problems possess. Okay? Bless you. Good. All right. So why are we doing this twice? Why do we have a second lecture doing kind of the same thing as Wednesday? Well, there's a few reasons. So one reason is just that, this is sort of, in every respect, a bit different. Okay, I really think this is a distinct implicit assumption people make when they do clustering. And so we get a different formal definition. We're going to talk about different algorithms. And we'll see some similar things in the analysis, but the proofs aren't the same either. So we'll see a host of new ideas. The second reason is that, just out of academic honesty, I want you to be aware that, Wednesday's notion is not the only notion of stable clustering. Actually, this has been a super hot area for about 5 years. There's at least 5 different candidates. They all have, roughly the same spirit, and you get roughly these same conclusions about strong enough stability implies tractability. And I wanted to show you that at least there isn't just one. Okay, there's a couple. All right, and on the homework, you'll explore the relationships between some of these. So that's another reason, just so you have some awareness of that diversity. Another thing which is kind of cool is that even though this mathematical definition is different than Wednesday, we'll see that it winds up imposing similar types of structural rigidity on the optimal solution. It's again going to basically imply, and you'll see this in the proofs, it'll imply that in stable instances for big enough gamma, opt basically has to be a bunch of tightly knit, well-separated clusters, maybe modulo a few outliers. That's basically what we proved in the analysis on Wednesday. We'll see all those themes reoccur. So it's kind of cool seeing this different definition lead us to kind of the same point. And so relatedly, another reason why I want to do this twice is because, both of the definitions I'm showing you, plus the other 3 or 4 definitions out there in the literature, you look at any one of those definitions, and you're probably not going to literally believe any one of them exactly. Okay? You assume real data, might sort of satisfy it, but strictly speaking, will definitely violate, some of these definitions, at least for the parameters that we're talking about. So, if you're trying to, reason mathematically about some phenomena, like say clustering seems easy in practice, obviously the holy grail would be you just write down this mathematical model that's uncontroversial. Everybody's like, oh yeah, you totally nailed what this is really about, and then you prove some awesome theorem that just like exactly matches what people observe. Okay? That almost never happens, once in a while, okay, once in a blue moon. But that's just not how it works, okay, in mathematical modeling. So you have to make some compromises, some overly strong assumptions to prove things. And so then you get nervous. You're like, well, is our conclusions an artifact of our assumptions, or are they actually sort of uncovering something real? So in lieu of one perfect model, a nice alternative is to have many models that are imperfect in different ways, all of which seem to be leading you toward the exact same conclusion. Okay? Then you start having, even though each model is highly questionable, the overall message from the suite of models starts looking believable. Okay? You start amassing some confidence in what these models are saying, like clustering is easy in many instances of interest. Okay? And so that's sort of another takeaway of these couple lectures. Okay? We'll get basically similar messages, takeaway messages from 2 different models. That reinforces our confidence in both of the models and their predictions. One final reason, this is a fun one to do and on top of the previous one. So last time showcased how making explicit an assumption in the data can lead you to exploit it in an algorithm. Right? So we came up with an algorithm on Wednesday we really never would have designed had we not written down that stability definition, probably. Now, the high-level ideas were pretty nice, distance thresholding and looking for number of common neighbors. Those are kind of high-level ideas, but the exact algorithm was definitely driven by the stability condition. Today, by contrast, we're going to show that a very nice novel twist on a very simple, very well-known clustering algorithm actually does get polytime solvability results for stable cable median instances. Okay, so here we're going to use this definition more just in the analysis of a known algorithm as opposed to drive new algorithms. All right, so any questions before we begin the technical development for today? Okay. All right, so let me just segue from that into, all right, so if we wanted to explain the performance of some simple, well-known clustering algorithm, okay, what's a simple, well-known clustering algorithm? So let me tell you about one. You might have seen this. I usually teach this in 161. It's called single link clustering. which might well win a popularity or at least kind of name recognition contest in a clustering contest. So how does it work? It's really nice, actually. So remember, we're doing like k-median or something like that. So you give me a metric space and you tell me k. So this metric space, I want to think of it as a graph. Okay? So the nodes are just the endpoints, and the distances are just edge weights. Okay? So it's a complete graph, a clique, weighted. The distances are the edge weights. Then what I'm going to do is I'm just going to run Kruskal's minimum spanning tree algorithm. Okay? So hopefully you remember minimum spanning trees. Maybe you forget which one's Kruskal, which one's prim. Okay? Kruskal's the one where you sort first. Okay? From smallest to biggest. You do a single pass through the edges. And if an edge is going to create a cycle with what you've already taken, of course you don't take it because you want a tree. But if it's not going to create a cycle, then you include it. And it fuses two connected components into one. Okay? Normally in Kruskal's algorithm, you want an MST, so you just run it until you have a tree, until you take n-1 edges. Here we don't want a tree. We want k clusters. So we're just going to stop it once we have k connected components, rather than just one. Okay? So that's single-link clustering. So run Kruskal's MST algorithm. I'm just going to write on the metric space, when I really mean on the complete graph with distances as edge weights. Stop when k connected components. Okay, so remember when you're including these edges one at a time, initially you have n connected components, just the isolated vertices. Each new edge replaces two connected components with one, so it drops the number of connected components by exactly one. Okay, so each edge addition of Kruskal's algorithm decrements the number of connected components. At some unique point we hit k. Okay. All right. So any questions about the algorithm? Clear what it is? I'll code this up in 10 lines of Python right now, or you have in the past, probably. Okay. So if we wanted to prove that a simple clustering algorithm works well in stable instances, it seems like the obvious thing to try to prove would just be to say, well, as long as gamma is sufficiently big, okay, we don't really have a feel yet for what gamma needs to be, but it's easier if gamma is bigger. So somehow, for some magical value of gamma sufficiently large, just run single-link clustering, right? That's going to give you k clusters. As we discussed, given the clusters, you can just separately for each one figure out which the best center is. And then you're just hoping that's going to, boom, be the optimal k-median solution. Okay? That would be kind of like the simplest possible thing that could be true, basically, about clustering stable instances. All right, well, it's not going to be quite so simple. Let me show you an example, which shows we're not quite off the hook. So suppose k equals 3, so we want 3 clusters. And m is going to be a parameter, and it's going to be big. Okay, how big? A million, whatever you want. And so here's what it's going to look like, the metric space. So there's going to be 4 groups of points, okay? And in a group of points, everybody's going to be basically co-located. Okay, so distance like epsilon between everybody in the same group. Okay? So m points, distance roughly 0. So that's a group. Same thing here. M points, distance roughly 0. M points, distance roughly 0. The one twist is going to be, this is going to be a tiny group over here. Tiny meaning, let's say 10 points. But again, basically co-located. Okay? Now, if only we had 4 centers, if only k was 4, we'd be golden, right? We just put 1 center in each group, and everybody would be distance 0 from some center. So our k-median objective would be like 0, right? But the problem is I've only given you 3 centers, okay? So intuitively, you're going to have to merge 2 of these groups into 1, okay? So suppose the edge weights are as follows. 10 on top, 2 on the left, 1 on the right. Okay? So take 30 seconds and figure out what the minimum objective function value of any k-median solution, any 3-median solution is. Okay, so just stare at the picture for a little bit.
What's it on the left?
That's a 2 on the left. So the way to think of it is, you've got you've got 3 superdense cities. You've got 1 superdense town, or really village. And then you've got kind of this path through them, where the path lengths are 2, 10, and 1. And basically, you're allowed to build 3 firehouses, and you want to minimize the sum of people's distances from the nearest firehouse. Okay? And again, if you could build 4 firehouses, no problem. Just build 1 in each city and also in the town. So what seems like, I mean, phrasing it this way, if I only let you build 3, it probably sounds kind of obvious where you should build them, right? I mean, you've got these like 3 cities of 1 million people, and then you've got this town with 10 people, okay? So the town with 10 people, okay, they'll be like 2 miles from a fire station, big deal, okay? So opt, I hope you agree, is like 20, right? So 0 for everybody there, 0 for everybody there, 0 for everybody there, 2 for each of those 10 people, okay? So that's the first thing to note. The optimal k-median thing is like 20. So single link clustering, okay, so it has to output 3 clusters, which means it's going to output a tree minus 2 edges, okay? So another way to think about this single link clustering is you sort of run Kruskel to the end, and then you kind of like rewind the last k minus 1 steps. Okay, so we're going to rewind the last 2 steps. So what were the last 2 edges that Kruskel would include in its tree in this instance? The 2 and the 10, right? Because it goes from lowest to highest, right? So Kruskel is going to output the clustering that you get after you delete these 2 edges, and the 1 is still in there. Okay? And remember, we're only allowed there's a correspondence between centers and clusters. So by virtue of fusing the 2 right-hand cities into a single cluster, now we're in huge trouble, right? Yeah, there's only a mile between them, but their populations are both 1 million people, right? Only one of them gets the fire engine, so now we have 1 million people a mile from a fire engine. Okay, so we get 1 million as our single link clustering objective function value. Okay? Total disaster. I hope you'll agree. Okay. Right. So single link is like M. All right. So now I owe you something else for this to be interesting, right? Which, I mean, we know k-median's hard in worst case instances, right? And somehow implicitly in this I've been saying, oh, look how easy it is. It's so obvious to tell what opt is, blah, 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 blah. But so the missing link, which I'll put as an exercise, it's just easy to check, is that actually this is a stable instance. Okay? It's actually a stable instance for gamma as big as you like. Okay? For every gamma, you can take M sufficiently large so that it's gamma stable. Okay? So, upshot, we started with like the nicest thing that could be true, right? Which is single link just works. Okay? Okay, that's false. It's time to take a step back. Now maybe we say, okay, well, can we have just like a not too, can we have a nice little twist of single link, which always works? Okay? And the answer is going to be yes. Right? And it's both a nice twist on single link, so it's kind of a nice extra idea, and then also it's just cool that this will work. Okay? Okay. So, any questions about the example? Everyone agrees vanilla single link is not good enough. Okay. All right, then let me introduce you to what I'm going to call single link plus plus. The authors don't call it that. Probably they should have. Probably more people would know it if they called it that, but I'm going to call it that. Single language plus plus by Bloom, Balkin, and Vempala. They came up with this algorithm in a different context, but it sort of works out of the box here, which is cool. So, and this is just nice, actually. This is a nice idea. So, what we do in the first step is we run Kruskel till completion. Okay? And what I want to point out to you is there's a really nice way to think about the tree that Kruskal builds up edge by edge as what's called a hierarchical clustering. Okay? And I think if I show you a simple example, you'll see exactly what I mean. So consider the following 5-vertex graph. With the following edge weights. So we're going to run Kruskal on that. So we sort from low to high and we let it go, right? So first thing happens is the 1 gets chosen by Kruskal. Okay? So U and X used to be connected components. They get fused into 1. So now over here, I'm going to start drawing a tree from the bottom up. So this is U and X. These are the 2 nodes we just fused. They're going to have a parent, which I'm labeling with the edge, or rather the cost of the edge that joined them. So the 1 edge, when Kruskal included it, fused the U and X into 1. Okay? What does Kruskal do next? Well, next Kruskal takes the 2. Okay? Fusing the V and the Y. Okay? Next it takes the 3. Okay? Which fuses together the UX component and the VY component. Okay? Or equivalently, fuses together the 2 connected components represented by these subtrees. So now these 2 are going to get a parent, which I'll label with 3. Okay? So these are just the node. These correspond to the edges included by Kruskal in the order that it took them. Now when Kruskal gets to the 4, that would create a cycle. So Kruskal skips that. Then Kruskal goes to the 5, and it picks the 5. Okay? And the 5 joins together the hitherto lonely Z with this big other component. Okay? So we have a 5 there. Okay? So notice, and I think you'll find it very easy to believe that these properties hold no matter what the graph is. So this hierarchical clustering tree on the right in purple, it has exactly n leaves, and the leaves correspond exactly to the nodes of the original graph G. So let's call this G, and let's call this H. Okay? So G has n nodes. H has n leaves, which are exactly the n nodes of G. The internal nodes of H correspond exactly to the edge additions by Kruskal. Okay? So each time Kruskal adds an edge, you add a node to H, which then has 2 children. Okay? So there's n-1 edges in a tree, and there's n-1 internal nodes in H, corresponding to the n-1 minimum spanning tree nodes. Okay? Also, if you look at subtrees of H correspond exactly to, so if you look at the leaves of a subtree, the leaves of a subtree were at some point in the execution of Kruskal a connected component. Okay? So like here's a subtree. It has the leaves U and X. So the claim is at some point UX was a connected component in Kruskal. And it was. Right after the first edge addition, it was UX. Okay? Same thing here. If I think of the subtree starting at 3, I get UXVY. So the claim is at some point that was a connected component in Kruskal, and it was just before the final edge addition. Okay? So there's also a total correspondence between subtrees in H and connected components that ever showed up in Kruskal. And the number of these things is exactly 2n-1. Okay? So here there are n leaves, n-1 internal nodes. That's one way to see it. Also, if you think about Kruskal, initially you start with n connected components. In each of the n-1 relevant iterations, you destroy 2 old ones and introduce 1 new one. So that's a total of 2n-1 over the course of the algorithm. Okay? So again, correspondence between nodes of G, leaves of H, connected components of G, subtrees of H. Okay? And internal nodes of H, and tree edges in G. Is all of that clear? Okay. So this is just a really nice way to kind of think about Kruskal's execution. So how are we going to make use of it? So here's what we're going to do. So single link without the plus plus, again, I told you one way you could think about it was you run Kruskal to the end, and then you rewind the final k-1 iterations. Okay? And you get k clusters. But now that we have this tree that we're looking at, it's going to allow us to visualize many different ways we might delete k-1 edges from the MST and get various k clusterings. Okay? What we did before will be one option out of many. So, by a k pruning of H, what I mean, so again, this is H. I mean, you delete k-1 internal nodes starting from the top. I'll say a little bit more what I mean about this in a second. Right, so if this is a set S, from the top, what I mean is that if a given node is an S, it should be upward closed. Then its parent is also an S. Okay, so S here, the nodes we're removing from this tree. Okay, so let's just start super simple. Okay, so let's just say k was 2. Okay, if k is 2, there's actually only one possible 2 pruning. Okay, because I have to delete from the top. Okay, so that means if I'm going to take this tree, this hierarchical clustering, and get 2 clusters out of it, the only thing, by definition, this is my definition, the only thing I'm allowed to do is kill off the 5. Okay? And that gives me a partition into UXVY and Z. Now, if k equals 3, and I'm allowed to delete 2 nodes, then I have 2 options. Okay, in this tree, actually, I don't have 2 options. But let's say in a balanced tree, like this, if I'm going to delete 2 nodes from the top, I have 2 options. Okay? Definitely I'm stuck deleting the root. Okay? But now I can delete either the left child of the root or the right child of the root. Okay? Each of those gives me an induced 3 clustering. Right? So if I delete this one, then that's the induced 3 clustering. On the other hand, if I delete this one, then this is the induced 3 clustering. Okay? So clear what I mean? So you delete k-1 from the top. Notice it's a binary tree, so every time I do a deletion, it shatters the tree into one more component than I had before. So k-1 deletions do indeed give me k clusters as desired. Okay? Okay. Another way to think about this, right, so imagine you delete from the top, right, you keep shattering this tree into subtrees. At the end of the day, what do you have? At the end of the day, you have a partition of the n leaves of the tree into k subtrees from the original graph. Okay? And actually, that goes the other way too. If you think about it, if you show me k subtrees that are disjoint and that are a partition of the leaves, by deleting everybody above them, that's what I get back. Okay? So in other words, what you can get top down by deleting k-1 nodes from the top are exactly the partitions of the leaves into k groups that correspond to subtrees. Okay? Everyone clear on that? All right, so back to single link plus plus. So the point is, we have a lot more options. Right, so single link, again, I was only allowed to go back and delete k-1 things in a unique way. I had to rewind Kruskal's algorithm. Now we see that as long as k is at least 3, I have options. And the plan of single link plus plus is to optimize over all of those options. Okay? So compute the optimal k pruning. Okay. So I'm going to leave for you to prove on homework 4 that this can be done in polytime. Okay, this is a relatively straightforward exercise in dynamic programming. Okay? And again, when I say optimal, right, so if you delete k-1 things, you get these k clusters. You pick the centers in the obvious best way for each cluster, and then you look at the k-median objective. Okay? So when I say optimal, I mean the one that induces the best k-median solution. Okay? With the optimal choice of centers. All right? So let's go back to our bad example, which broke the original single link clustering algorithm. So this is going to look a lot like our balanced tree over here. So now, instead of just aborting before the last two iterations of Kruskal, imagine we run it to completion. Okay? So obviously the first thing Kruskal does is it picks all of the zero-linked edges, and so all of the cities get fused together and the township gets fused together. So you've got your M, your M, your M, and your 10. Okay, these are the population sizes. And then what does Kruskal do? Well, it picks the 1. Yeah, that's right. Then it picks the 2. And then it picks the 10. Okay? So now, remember, k equals 3 in this bad example, so we're allowed to delete 2 nodes from the top. Okay? And one's got to be the root. Now, single link, where you rewrite Kruskal, that's going to delete just the largest ones. Okay, so it's going to ignore the graph structure, or the objective function is just going to say, what are the highest labels I can see? So single link would delete those, right? And that's why we wound up in this bad case with a single center for 2 cities of population 1 million. In single link plus plus, we're allowed to optimize over all of the options. Okay, granted, here there's only 2 options, right? There's that one and there's that one. But single link plus plus will consider them both, and it'll say, hey, that looks a lot better. Okay, so that's the one it's going to pick. All right? So certainly, it does fine in this example. That's all I've convinced you. I mean, it's obvious it can only be better than single linkage because the original single link k pruning is one option that it optimized over. So it'll always be better. The key point of this theorem, of this lecture, is a theorem that says, actually, this recovers the optimal k median solution in 3 stable instances, it turns out. Okay? So any questions?
Because it isn't clear that it would do much better in something like this, where you have to take the root and maybe z is very far away from.
Sure, yep, but then opt is going to suck too, so sort of not our problem. I mean, it's someone else's problem, right? So this is always what's funny, right? So when you have these objective functions and you're talking about computing the optimum or computing something close to optimum, an implicit assumption we always make in the analysis is that the optimum is actually useful, right? That you'd be happy to have the optimum. Not always true, right? But then that's sort of like an upstream, that says add more resources to the system, or like get rid of some of these constraints, or whatever, right? So in this class, we're just going to be happy to get the optimum, whether it be good or bad. Yeah. Good. Other questions? So that's going to be our algorithm. This is our protagonist for the day. Okay. I think it's a very nice algorithm. This has been, you can imagine coding it up. Other people have certainly coded it up. It's a nice idea. So rather than just commit up front to a single k clustering, generate this tree which implicitly encodes lots of different k clusterings which you can optimize over efficiently. Okay, very nice. Okay, so here's the theorem we want to prove. By Aswathi, Blum, and Sheffett. So for all gamma at least 3, single link plus plus computes opt in gamma stable instances. Okay. So you should be wondering, is this good or bad? Like, should I be impressed with this 3? So the homework will have some stuff to, help answer that question, but I'll just tell you the punchlines now. So first of all, this algorithm, so single link plus plus, does not necessarily recover optimum once gamma drops below 3. So as far as the analysis of this algorithm, gamma equals 3 is tight. It's the right answer. Okay? If you change the algorithm, it still has a similar flavor, but the linkage step is a little bit smarter. Then it's known how to get down to gamma equal to 1 plus square root 2. Okay, so like 2.414, okay, by a variation of the algorithm. And it's also known that forget about any particular algorithm, it's known it's NP hard to recover the optimal solution once gamma drops below 2. Okay, so no algorithm can get below 2. We know algorithms that can get 1 plus root 2. This algorithm gets 3, and that's as good as this algorithm does. Okay? So that's sort of what we know about this question. Right? Good. So let's turn to proving this. So here's how we're going to prove it. We're going to look at the algorithm. We're going to look at the single linkage plus plus algorithm. And we're going to ask ourselves, what has to happen for this to work, for this to have a chance of working? Okay? What are sufficient conditions on the input, or really on sort of the execution of this algorithm, that in the second step it'll actually be able to find the optimal solution? Okay? Then, once we have a good understanding of sufficient conditions for the success of single linkage plus plus, at that point we'll actually invoke the stability property and show that it implies the sufficient conditions. Okay? So for now, I don't want you to think about stability per se. I want you to think about this algorithm. Okay? Form this hierarchical cluster tree, and then among all ways of deleting k minus 1 things from the top, compute the optimal k pruning. And we're hoping one of those is indeed the optimal k median solution. When is that going to happen? So, sufficient conditions for success. All right, so suppose, again, so now we just have any k-median instance, and we're hoping that the best k pruning of this tree is indeed the optimal clustering. Okay, so when's that going to happen? So let C star 1 up to C star k denote the optimal clustering. So first I'll state something which is really sort of equivalent to it succeeding. Okay, the second one's just going to be a sufficient condition. This one's really an equivalence. So what has to happen? So what has to happen, so remember I told you that there was a bunch of correspondences between the graph G and the tree H. One of the correspondences was the subtrees, the 2n minus 1 subtrees of H correspond exactly to the connected components that show up at some point in Kruskal's algorithm. Okay? Now, when we take a k pruning, at the end of the day, what are we going to hand back as a clustering? It's going to be a collection of subtrees of this cluster tree. Okay? So we've committed to outputting subtrees of this thing. So for us to have a chance at outputting the optimal clustering, every optimal cluster better show up as a subtree in this tree. Okay? So this is really just sort of rephrasing a little bit what it means to succeed. So every C star I appears at some point in Kruskal. Okay? And again, remember that's really like two statements. First of all, our outputs are subtrees. Second of all, subtrees are connected components in Kruskal. Okay? So basically, as the analyst, we think of ourselves as knowing what the optimal solution is, right? And we have there's this cluster of 5 points, 3, 7, 10, 18, and 22, and we know what it is. And we're like watching Kruskal run with our fingers crossed, okay? And we're really hoping that this cluster shows up. What could go wrong? Well, okay, so suppose this cluster has 5 points, and suppose Kruskal's joined 3 of them together, okay? So that sounds good. But what can go wrong is if all of a sudden it joins some point from some other cluster before it gets to those last 2, we're host, right? Kind of components only grow over Kruskal. So if ever you get in one cluster points from 2 different clusters, 2 different optimal clusters, C star I and C star J, before you get C star I completely, done. You're never going to see C star I as a connected component in Kruskal. Okay? Okay, so that's what we're worried about. All right, so this is what we need. Oh, right, so what's the converse? So I argued that this is certainly necessary for the algorithm to succeed. Why is it sufficient? Well, if every C star I appears as a subtree, we compute the best collection of subtrees. So if the optimal is in there, we're going to find it. Okay, it's going to be one of the things we optimize over. Okay, so this is if and only if. So now let's just take this on faith. This is our new goal. Okay, this is our new success criterion. What's a sufficient condition for this to happen? For every optimal cluster C star I, comprising however many points, we want exactly that set to show up as a connected component at some point in Kruskal. When will that happen? Well, so here's going to be our final condition. I claim that if this property 2 holds, we're golden. Okay? Single link plus plus is going to work. Consider an optimal cluster, C star I. And consider a strict subset of it. Okay? So like A here, those are the 3 points out of the 5 that we had so far. That's what you should think of them. Okay? We're really hoping these other 2 will get joined with this cluster. We're really scared that points from some other C star J is going to get joined first. Okay? So for all strict subsets of the optimal cluster C star I, the condition that will be a sufficient condition for correctness is that the closest point, I'll draw you a picture in a second, the closest point to A, remember X is the set of all points, so the closest point to A, not counting those already in A, lies in C star I, not outside of C star I. Okay, so here's the picture you should have in mind. We've got A. Okay, these are the 3 points we've got so far of the cluster. These belong to some bigger cluster C star I. There are various points not in A. Some of them are in C star I, some of them are not. Like, for example, maybe this is a C star J. And this condition says the nearest neighbor to A better lie inside C star I and not outside. Okay? So I claim this is a sufficient condition. If 2 holds, then 1 holds. Okay? That's what I claim. Why is that true? So let's say notes. 2 implies 1. So here we're really going to use properties of Kruskal. The Kruskal really considers the edges from shortest to longest. So imagine, so consider your favorite C star I, okay, some cluster, and fast forward Kruskal until the first time that some edge is chosen with exactly 1 endpoint in C star I. Okay, 1 endpoint in C star I and 1 endpoint outside of C star I. That's got to happen sometime, right, because Kruskal eventually merges everything together. Okay, so at some point stuff in C star I gets merged to other stuff. So look at the very first time that that happens. Okay, it hasn't happened yet. All right. Now, what the claim is, C star I has to be complete by this point. Okay? Because if it wasn't, then we'd only have some strict subset A of C star I. Okay? And instead of joining some point outside of C star I, we join the closer one, which is inside C star I. Condition 2 says that that point must exist. Okay? If you don't have all of C star I yet, the closest thing to you, i.e. the next one considered by Kruskal, lies in C star I, not outside. Okay? So that means the very first moment at which you pick an edge that's in and out of C star I has to be complete. Okay? It must be the case you've already connected all of C star I together. Okay? So that's why 2 implies 1. Okay? So any questions about that? All right. So just where we are, here's what we want to prove. We want to prove single link computes opt. What we've shown is that if the input satisfies property 2, then single link plus plus computes opt. Okay? So stable or not, whatever the instance is, if this is true, and notice this is not about the algorithm, right? This is a statement just about a metric space. Okay? There's some optimal clusterings, the C star I's. You can just enumerate over all A's and check if this holds or if it doesn't hold. If this always holds, boom, we're done. Our algorithm works. Okay? So the missing link, all we have to do left in the lecture, is prove that if an instance is stable, 3 stable, then this condition is guaranteed. Okay? That's all that remains. Everyone with me? All right. So, to do, ooh. This totally goes the wrong direction, doesn't it? No, that's the right direction. That's the right. Never mind. Notes. Well, let's say to do. Three stable implies 2. Okay? So that's the rest of the lecture, establishing that. Making the link between the stability of k-median instances and the sufficient criteria for success for single link plus plus. All right. So there's going to be 3 steps, each, none of them too bad, but each slightly trickier than the first one. Why don't you take a minute? I'm going to write down the first step. Take a minute to think about this and discuss it with your neighbor if you want. So what we're going to do now is we're going to start from the stability property. So we're going to have a stable instance. And so what we're doing now is really going to have the same feeling of the exercise we did on Wednesday. We said, OK, we have this instance. We know it's stable, but the stable references this optimal solution. And we can't compute the optimal solution. Or that's sort of circular. We're trying to compute the optimal solution. So how do we actually use this? Right? So we're going to start from the stability property assumption and derive a bunch of consequences that are a little easier to work with. OK? So here's the first one. So suppose you're 3 stable, and again, remember what this means. This means you're allowed to blow up distances any way you want between a factor of 1 and 3, and opt stays exactly the same. Okay, that's what 3 stable means. If an instance is 3 stable, then we get something which looks a lot like the well-separated condition we had on Wednesday. Okay? So for all points in the ith optimal cluster, again, we don't know what this is. This is just for the analysis at the moment. For all x and c star I, if I look at a cluster center for some other cluster other than x's, it's going to be way more far away from x than x's cluster in its center I. Okay? Specifically, it's at least triple the distance between x and its own center ci. Okay? So here, just to make sure the notation's clear, there are these optimal clusters, c star 1 through c star k. Ci and cj are the centers of those optimal clusters. X is some point in cluster I in the optimal solution. Okay? So this is saying like well separated. Okay? The centers to which points are assigned are way closer than the second best option. Okay? So take a minute and see if you see how to go from the stability assumption to this conclusion. It's not trivial. It's a few lines, but it's not straightforward. All right, so let me show you the proof. So sort of the problem you have to solve and come up with the proof is how do you invoke the stability condition, basically, right? So that it sort of gives you this freedom to kind of blow up distances, and then you have to start thinking, okay, like what would be a useful subset of distances to blow up in some way, okay? So what turns out to work well here, especially kind of given the clue of the statement, is what we're going to do is we're going to take the cluster C star I, okay, and we're just going to blow up all the distances inside C star I by a factor of 3, by the biggest that we can, okay? So blow up distances inside C star I by 3. Okay? So for example, this distance does not get blown up. Okay? Because Cj is in a different cluster. Okay? So only if both points are in C star I do you get blown up. So that doesn't get blown up, but this does. Okay? Because they're both in C star I. Okay? So by stability, op stays the same. Okay? This is actually the only time we'll ever invoke the stability hypothesis in the entire lecture, because it's 1 point. Okay? So op stays the same. So opt is C star 1 up to C star k. And so the clusters stay the same. The centers also stay the same. Right? Because given a cluster, what's the best center? Well, you just try them all and see which one minimizes the sum of the distances. Inside C star I, all the distances scaled by the same amount. So same cluster is optimal, namely Ci. And because it's optimal, it also means that you do better assigning x to Ci than to Cj. Okay? What does that mean? That means x's distance to Ci, even after the blow up, is smaller than its distance to Cj. But that's exactly what this inequality says. Okay? This inequality says that this distance, even blown up by a factor 3, still is less than the distance to Cj. Okay? So that's step 1. And again, you saw something like this on Wednesday. Okay? And I basically think it's a feature that we're seeing similar structural constraints emerge from a different definition. Okay? Actually, I find this pleasing. Okay, so you're much closer to your center than the second best center, is what this says. All right, step 2.
Quick question.
Yep.
So just to be clear, the CJs are possibly different for all the x's.
Possibly different for all the x's.
So like x could be one x in CI can be closer to,
So I guess I should say for all j not equal to I. That would certainly be a more precise statement. Does that answer the question? Or?
yeah.
Yeah. Yeah. So every single center other than your own is far away. Yeah. So in particular, the second best one is. Yeah. Thanks. Okay. All right. So now, so this is sort of saying everybody's close to their center. So now we're going to have a step which says points in different clusters are far apart. Okay? Which again is something we were basically getting at on Wednesday in a different model. So suppose x is in C star I, and y is in C star j, with I not equal to j. The claim is that they're far apart. How far apart? More than double the distance of either of these points to its own center. Okay, so sort of like Wednesday, we're kind of like normalizing distances. So one question with a distance is like what's close and what's far. Like, is 10 close or is 10 far? Well, it depends. What do the other numbers look like? So we're kind of normalizing by, you know, distances between points and their centers. So relative to the distance between x and its center, or if you like, the distance between y and its center, the distance between x and y is way bigger than that. Okay, it's at least double the distances between either of these 2 points in their respective centers. Okay? So that's the claim for step 2. Okay, why is it true? All right, so we're going to look at the following picture. So remember, x is in I's cluster, y is in J's cluster. All right, so what do we know? What do we just inherit from step 1? Well, step 1 says you're far from a center that's not your own. Okay? So between x and Cj, that's going to be at least 3 times the distance between x and Ci. Right, that's by step 1. Also by step 1, the distance between y and Ci is going to be at least 3 times the distance of y and Cj. Okay? So that's just from step 1. Yeah.
What's the thing in the top right say?
For all I not equal to j. This?
Yeah.
I not equal to j. Okay, so now we also have the triangle inequality, which says that if the straight path between Ci and Cy is big, then so is any two-hop path that starts at Ci and ends at y. Okay, and similarly for x and Cj. So what does that buy us? So by step 1 in the triangle inequality, we have right, so if you go from y to Ci via x, that's lower bounded by the distance straight from y to Ci, which is at least triple the distance between y and its center, Cj. Okay? Similarly, if we go from x to Cj via y, that's lower bounded by the straight line distance between x and Cj, which by step 1 is at least triple the distance between x and its own center, Ci. Okay? So that's just that picture on the right plus triangle inequality. Okay, and now we're done. Okay? So assume, there's 2 cases, they're symmetric, so I'm just going to do one of them. So assume, for example, that this is bigger than that. Okay, that x is closer to its center than y to its center. Okay?
That says X is farther.
You're right. You're right. Suppose the distance is bigger between X and CI, between X and its center than Y and its center. And then, let's look at 2. So remember what we're trying to do. We're trying to lower bound the distance between X and Y. X and Y are in different clusters. We're just trying to say they're far apart. Here are X, Y distances. We're trying to get a lower bound. We have a lower bound. That's good. What do we want to do? We want to subtract off this term. Okay? So we have triple the distance between X and CI minus the distance between Y and CJ. But the distance between Y and CJ is smaller. So it's 3 times something minus something which is less than 1 times something. So we're left with 2 times that thing. Okay? So we get d of xy. So this is from 2 with the red assumption is at least 2 dxci. Okay? So that's this part. Oh, but then actually dxci was bigger than dycj. So I guess we got to fit the other one too. Okay? It's bigger than that, that's bigger than that, so we're done. Okay? So, whatever, there's some triangle inequality maneuvering in there. I don't expect you to remember the details, but what the statement says is nice, right? Different clusters, you're far away. Right? Okay, so step 3. Third and final step, happy to say. Okay, so we are going to use this property. So are we? I forget. We already used it. Maybe that was good enough. All right, so we've got every point is close to their own center. Pairs of points in different centers are far apart. So once again, we've derived that opt has to be these tightly knit, well-separated clusters. Now let's seal the deal. Let me remind you, you probably forgot about this. This is the condition we're shooting for. Right? We had this part of the lecture where we said, when does single link plus plus succeed? We did a little bit of work, and the payoff was we got this sufficient condition. Okay? This sufficient condition says, what we really want to be true about this metric space is if you have an optimal clustering and you have a strict subset of that optimal cluster, the nearest point should be something else inside the cluster, not outside. So now let's verify that fact about 3 stable instances. Okay? So we're going to prove that this is true, prove that this condition holds, using what we have in step 1 and step 2. All right. So step 3. To verify this condition, 2, pick your favorite optimal cluster C star I, pick your favorite strict subset A. Okay? First thing to note, suppose the optimal center of this optimal cluster is not an A. Okay? Then I claim we're done by step 2. Okay? Why? The claim is CI. All right, so I should give you a picture here, right? So what we're talking about right now is we have C star I, and we have our subset A. And at the moment, we're thinking about the case where the center is outside of A. Okay? Good. Is it step 2? Yes, yes. So what did we just prove in step 2? We proved that anything outside of C star I is far away from anything in C star, sorry. Any points from C star I and C star j are far apart. What does far apart mean? It means double the distance from each of their distances to their respective centers, right? Well, everybody here is close to their respective center. Everybody outside is far apart. Okay? So the point is, if the center of the cluster is outside of A, I mean, that's already a super nearby point to stuff in A, okay? Because everything's close to the center. So that's the easy case, okay? So if C is outside of A, that's your certificate that it's closer than anything outside of C star I. So CI close enough, done. All right, so now from henceforth, we'll assume that CI is an A. All right? And this case is a little tricky. All right, so for contradiction, what we're ultimately going to contradict is step 1. So step 1 says that everybody's 3 times as far at least from other centers as they are from their own. Okay, so that'll be the contradiction. So for contradiction, we're assuming 2 is false. This is false. So suppose closest point to A of everybody else is Y, which is in some other C star J. Okay? So we have C star I, we have CI, we have A, we have C star J. Okay? And then suppose X is the closest point to Y, anywhere in A. Okay? Suppose closest to Y in A is X. So we have X right here. We've got this allegedly quite close Y over here. Okay? So we're assuming close, basically. Okay, that's how we're starting the contradiction. Now, let Z, and I promise this is the last one we need, let Z be what we were sort of hoping would be closer to A. Remember what the condition says. The condition says, look at the nearest neighbor to A. We want it to be in the cluster C star I. A is a strict subset, so something's not in A yet. We want that to be the closest. Right now we're assuming it's not. But let Z be some candidate. Okay? So any point of C star I minus A. Okay? So Z is going to be like, maybe it's all the way over here or something. Okay? So that's the setup. So now I've got all the notation, and we just got to kind of get the triangle inequalities right. Intuitively, here's where we're going. Okay? So this is some distinct cluster. It has some center Cj. Now here's what step 1 tells us. Okay? Here's what step 1 tells us about every point, in particular point Z. Step 1 was this well-separated condition. You're way closer to your own center in the optimal than any other center at all. In particular, Z, we know this, Z is much closer to Ci than to Cj. On the other hand, under our current assumptions, we can construct a quite short path between Z and Cj. Why? Well, we can go from Z to Ci. That's close because it's just a point to its center. We can go from Ci to X. Again, that's between a point and its center, so that's small. By assumption, X and Y are pretty close to each other, so that's not too big. But then from Y to Cj, that's also just from a point to its center. So we have these 4 hops, all of which we have some control on the upper bound side of why they're not too big. But on the other hand, how can it then be that Z and Cj are super far apart? Okay? I mean, that is really the proof. I mean, to see where the 3 comes from, we'll have to actually do the computation. But conceptually, that's exactly the proof. Okay? So the contradiction is what gives us an upper bound control in the distance between X and Y, which is the missing link on this 4-hop path. Okay? Good. All right, so we don't need this condition anymore. Remember, this is what we took the contradiction of, so the contrapositive of this, the negation of this shows up on the right board. So all we need to do is exhibit the contradiction, which is getting the triangle inequalities just so. Okay, so like I said, the contradiction is going to be, Z and Cj should be far apart by step 1. Okay, so to contradict that, we're going to take the distance between Z and Cj, and then we're going to construct this 4-hop path on the right-hand side. Okay? So we go from Z to Ci, plus Ci to X, plus X to Y, plus Y to Cj. Okay? Triangle inequality, that's an upper bound, 4-hop path. Okay? Now, what's our control over these things? Here's what we're going to do. So, right, so that I want to leave. This is going to be for the contradiction. And these I want to relate in this. Okay, so we've got these 4 different terms. Let's take these 3 and collapse them into one. How do we do that? Well, what did step 2 say? Step 2 said that the distance between 2 points in different clusters, such as x and y, is big. Big relative to what? Big relative to the distances between x and y and their own clusters. Okay? Factor 2 difference, actually. So here's the distance between x and its own cluster, distance between y and its own cluster. Right? This is twice as big as either of those. Okay? Or if you like, each of these is at most half of that. Okay? So most half dxy and most half dxy. Okay? So we can collapse all this into at most 2 dxy. Okay? This is using step 2. Okay? Now, this is sort of a clever bit, and we're basically done now. This is the last clever bit. So how do we relate the distance between z and its center to the distance between x and y? These don't seem to have that much to do with each other. Here is where we use the fact that, the definition of y. What is y? Y is the closest point to A. Right? We haven't used that property of y yet. Okay? Remember how we do it. We started by contradiction. We have this set A. What's the nearest neighbor? Call it y. If it's in C star I, we're done. If y is outside of C star I, we're in trouble. Okay? So it's the closest point to A. Well, here's another point outside of A. Z. We could have chosen Z. We would have been very happy, actually, had we chosen Z, because that's inside C star I, which we want. We chose Y instead. Why? Evidently, so this is by our initial contradiction, it must have been that the distance between x and y is at most the shortest distance between Z and its nearest neighbor in A. In particular, remember this is the case where the center is in A. So one choice for Z's nearest neighbor in A is the center CI. Okay? So CI and Z, summarizing, CI and Z is a particular choice of a point in A and a point outside of A. X and Y, by definition, are, amongst all points in A and outside of A, the pair that minimizes the distance. So dxy is at most dzci. Okay? So that means we can take this double distance x and y, upper bound this by the distance, right? What does this say? Upper bound this by the distance between z and ci. So that gives us on the right-hand side a triple distance between d and ci. This is exactly what step 1 said could not happen. You could not have a second best center within a factor 3 of a second best center. Okay? See you Wednesday.